Hello there, it's Muhammad Hamdi, and in this video I'm going to talk about old ceramic restorations. I'm going to talk about the materials, the types of crowns used in old ceramic restorations, and let's get started. Okay, here we have old ceramic restorations. Okay, let's talk about the oldest model of old ceramic restorations. In 1886, Land introduced the first old ceramic crown utilizing the platinum foil technique known as porcelain jacket crown. What is meant by porcelain jacket crown? Porcelain jacket crown, it is a platinum foil used to cover the whole die of the restoration, the whole die of the tooth. The whole die is covered by platinum foil. Then the porcelain layers are placed on it, layer by layer. Okay. Then the platinum foil removed from above the die, and then placed into the furnace to fire the ceramic. Okay, and this is an old technique. Then the acrylic resin was introduced in 1940, and the introduction of acrylic resin decreased the popularity of the old ceramic crowns because of the high brittleness of the old ceramic crowns. Old ceramic crowns are very, very brittle, and less liability of acrylic resin to fracture. Okay. Okay. Then we have the acrylic resin disadvantages. Acrylic resin suffer from the following disadvantages: high coefficient of thermal expansion and contraction than tooth structure, 7 to 8 times, high wear, and so low wear resistance, discoloration, and monomer irritation, because acrylic resin contains monomer. Okay, we have discoloration of the acrylic resin and low hardness of the surface. Then we have the PFM. Since the development of porcelain fused to metal procedures in the early 60s by Dr. Abraham Weinstein, we have represented the gold standard of prosthetic dentistry, thanks to their good mechanical properties, as we have a metal cupping. So the metal cupping increased the mechanical properties and somewhat satisfactory aesthetic results by the superstructure of the porcelain on the metal, so give some satisfactory aesthetic results and clinically acceptable marginal and internal adaptation, as the metal has better marginal integrity and marginal adaptation more than the porcelain. So it is acceptable in the clinical practice for marginal adaptation and marginal integrity. Then the porcelain fused to metal disadvantages: low biocompatibility, because it has metal, and the metal are very close to the soft tissue, gingival margin. Okay, and low aesthetics because of the color band, color band, or the margin. Here is the margin of the metal are discoloring the gingiva. Okay, all ceramic restorations, they increase the demands for porcelain restoration because the PFM, it is not perfect for aesthetics. So increase the demands for porcelain restorations to have an acceptable aesthetical restoration, properly aesthetic restoration. Okay, the advantages is high aesthetics. The advantages are high aesthetics, high biocompatibility, chemically stable, and supragingival finish line. Supragingival finish line. Why? Because the porcelain have the same color of the tooth, so it is not important to cover or to mask the color of the metal by deepening the margin below the gingival margin to cover the margin. So we didn't have to make it subgingival. It is okay to make it supragingival now for all ceramic restorations because it has the same color of the tooth structure. Okay, the dental porcelain. What is ceramic? Ceramic, any product made. We have some definitions here. Ceramic. What is ceramic? What is glass? What is porcelain? What is dental porcelain? Okay, ceramic, any product made essentially from a non-metallic material. Non-metallic material by firing it at a high temperature to achieve desirable properties. This is called ceramic. Non-metallic materials fired at high temperature to gain the desirable properties of the material. The glass, what is glass? Any product, a product results when its entire components, when fired, fuse together. Its components fuse together when fired to form a single transparent material. This is glass. What is porcelain? Porcelain refers to a family of ceramic. So what is porcelain? Porcelain, family of ceramic materials composed essentially of kaolin and quartz feldspar and fired at high temperature during the manufacture to form a glassy material, then rapidly cooled by quenching in water, producing a fret. The particles of the porcelain material, it is called a fret. Dental porcelain, it is the type of clay that has translucent body and transparent glaze. Translucent body of the translucent, we will know, and we will go deep in the structure of the porcelain crown and know what is the body of the porcelain or body of the crown, and transparent portion or enamel porcelain. Okay, okay, that's okay. Conventional dental porcelain consists of glass matrix phase and at least one crystalline phase. Let's know, or let's learn what is the glass matrix phase and what is crystalline phase. The glass matrix phase, which is responsible for what? Responsible for the transparency of the material. Glass matrix, high glass matrix phase, high transparency. So let's know the dentine porcelain. We have two types of porcelain. Let's say we have two types of porcelain: dentine porcelain and enamel porcelain. Which of them is more transparent? The dentine porcelain or enamel porcelain? Logically, the enamel porcelain, because enamel porcelain means the enamel layer or the porcelain layer which resembles the enamel structure and the transparency of the enamel structure. So the enamel porcelain has glass matrix phase, high glass matrix phase. So enamel porcelain has higher gloss matrix phase than that of the dentine porcelain. So the higher the glass matrix phase, the higher the transparency. The higher the crystalline phase, the higher the opacity. Okay? Okay. So glass matrix phase here, which is responsible for the transparency, and here the crystalline phase, which is responsible for what? For the opacity. Okay. الكومبوزيشن Feldspar 70 to 90%, silica quartz 11 to 18%, kaolin and other ingredients, coloring pigments, and lanthanide oxide for fluorescence. Okay, that's not very important. It is old, the conventional porcelain, and now it is not very used in the dental practice. So let's go into the composition more deeper. The Feldspar is composed of anhydrated aluminum silicate. Anhydrated aluminum silicate. Aluminum silicate, but anhydrated. Doesn't have water molecules. So it is anhydrated aluminum silicate, naturally occurring substances. So the ratio between the potassium aluminum silicate potash and sodium aluminum silicate soda will vary. So the Feldspar composed of two main molecules, two main components: the potassium aluminum silicate with sodium aluminum silicate, potassium aluminum silicate with sodium aluminum silicate, potassium aluminum silicate called potash, and sodium aluminum silicate called soda. Okay, the Feldspar, the rule of the Feldspar, what? On heating under fusion, forming glassy material which gives the porcelain its translucency. So during heating, they are fusing together. They are fusing together to form a glossy material, which gives what is the function, or what is the aim of the glossy material? It is responsible for the translucency of the porcelain. Okay, and acts as matrix to hold other components like crystals, or other components like a kaolin or any other component. Then we have the potassium and sodium oxide provided by Feldspar. The glass modifiers. The glass modifiers, what are the aim of glass modifiers? Soda reduces softening temperature of the glass. Reduce the softening temperature of the glass. And the potash increases viscosity and hardness of the glass network. Therefore, prevent pyroplastic flow of the porcelain to obtain the desired configuration of the restoration during manipulation, or during layering of the porcelain. So during a layering of the porcelain on the die, we have the die here. Let's say it is the die. Okay, we have here the die, and the die, we will layer a porcelain layer by layer. Okay, if it is pyroplastic porcelain, naturally pyroplastic material, when it is mixed with water, have a pyroplastic flow property, means flow. Okay, so we don't want to make it flow, so we can't make the landmarks and make the grooves or make the anatomy of the tooth, because it is flowable. So we add the potash to increase the viscosity of the glass network. So if we put a layer of porcelain, it will stay in its place on the die and don't flow away from the die. So if it is viscous because of the potash, it will retain it in its position, okay? And the hardness of the glass network therefore prevent a pyroplastic flow to obtain a desired configuration of the restoration, and increase the coefficient of thermal expansion to be compatible with the metal. Increase a coefficient of thermal expansion to be compatible with the metal. The potash, we have a property called the coefficient of thermal expansion, which is responsible for the expansion or contraction of the material if it is heated, okay? So the metal have a specific coefficient of thermal expansion, and the porcelain has lower coefficient of thermal expansion. So the potash is responsible for increasing somehow the coefficient of thermal expansion to be compatible somehow to the coefficient of thermal expansion of the metal. So if the metal, let's say we have a hot drink, and if there's big difference between the coefficient of thermal expansion of the two materials, metal and porcelain, the porcelain will contract or expand in different amount, or in different or bigger amount or lesser amount than of that of the metal. So it will fracture, it will debond from the metal, and it will fracture. So we have to make the coefficient of thermal expansion of the two materials, of the two different materials, be somehow compatible to each other, okay? So the potash is responsible for it, okay? Now we have the silica. Silica, we have pure quartz crystals, and should be ground to the finest grain size possible. The silica should be what? Finest grain size possible, and we will know why it should be fine, okay, or large. Maybe the silica, it is the crystals. It is what? The crystals. The Feldspar is the glass matrix phase, and here's the silica is the crystals or crystalline phase. So it should be fine. The particles of the crystals should be fine as possible as we can, okay? The rule silica remain unchanged during the firing, therefore form a network for other ingredients, so glass bridges increase the strength. So silica is responsible for increasing the strength of the porcelain, okay? So we have different, if we have different crystals, we have different strengths of the porcelain, okay? Then kaolin and clay. And the rule is when mixed with water, kaolin or clay, when mixed with water, it becomes sticky, therefore forming a workable mass of porcelain, increases the workability. Okay, kaolin and clay increases the workability of the material and adds to the strength of the mass, adds strength, more strength. But what is the responsible for the strength of the porcelain? What? I'm hearing you. Yes, the crystals or the silica, okay? And kaolin and clay increases the opacity if more than 10%, okay? If we added kaolin or clay more than 10%, it increases the opacity. So it is not preferred to increase more than 10%. And then the coloring pigments. We have different types of dental porcelain according to what? According to some categories, okay? According to firing temperature, we have, it is divided into 4 types. The high fusing means high temperature, high fusing temperature, medium fusing, and low fusing, and ultra low fusing. A high fusing for what? For manufacturing a porcelain denture technique. A porcelain denture have frameworks, partial denture frameworks, or partial denture for removable partial denture frameworks, or partial denture, or fixed dentures, fixed denture, porcelain fixed dentures. Okay, and it is not very common, yani. Okay, then medium fusing for manufacturing jacket crown, medium fusing temperature for manufacturing jacket crown, and low fusing for veneering in metal ceramic crowns, and ultra low fusing for veneering titanium and titanium alloys. Just know about them, and it is not very, very important to ask about or to know. It is a technician responsibility. Okay. Then we have the porcelain manipulation. The porcelain manipulation. Okay. Mixing, just mixing powder and water, and we have some companies bring its liquid, its special liquid, have some more ingredients. Okay, some types of the binders, maybe distilled water, propylene glycol, or water-based glycerin. Okay, it is not very important here. Okay, the application by using a brush or spatula to carry the mix and build the restoration to the desired form and contour is done in layers associated with continuous removal of excess water. The porcelain condensation. Why? To remove the water between the particles, to make the porcelain layers condensed on each layer. Okay. On each other, so it will compensate that during firing the water will evaporate, so it makes the porcelain porous, so we don't want it. So the condensation prevent that problem. Okay, the condensation, it is the removal of excess water. What is meant by condensation? Removal of excess water from the porcelain working mass after its application and before firing, aiming to what? Aiming to decrease the firing shrinkage. We want to decrease the firing shrinkage and decrease the porosity for better aesthetic and color properties, and increase the adaptation and strength, more closely packed particles, as we said before in the previous slide. Okay, here we have the requirements of alloys used in metal ceramic restorations, and we have some specific requirements for the alloys. The alloys must have a high melting temperature greater than that of the fusing temperature of the metal of the porcelain by 170 Celsius degree, and then firing temperature, as we said, then firing temperature of the ceramic and solders. Okay, and then the coefficient of thermal expansion and contraction of the ceramic and metal must be compatible. As we said before, the metal is slightly higher than, the metal should be slightly higher than that of the ceramic, thus putting the ceramic in compression where it is stronger. Ceramic is stronger in compression, but it is brittle. It is weaker in tensile strength. So in compression strength or on compressive strength, it is strong. So we can make it strong by putting it in compression, by make slight difference between the ceramic and the coping metal, the metal coping, by making the metal slightly higher than that of the ceramic, where it is stronger following cooling, and as we said before. Requirements of veneering porcelain. Requirements of veneering porcelain, we have the compatible with the alloys in the terms of fusing temperature of ceramic with coefficient of thermal expansion. We should the ceramic should be compatible with the alloys under it, in terms of the fusing temperature and the coefficient of thermal expansion. Fusing temperature, what? The fusing temperature of the ceramic should be lower than the melting temperature of the metal by lower than the melting temperature of the metal by 170 Celsius degree, and the coefficient of thermal expansion of the ceramic should be slightly lower than the coefficient of thermal expansion of the of the metal under it, beneath it. Okay, chemically and optically stable during firing. Must be chemically and optically stable during firing. This is the porcelain. Okay, ceramic should have high viscosity, as we said before in previous slides. We mentioned that the ceramic should have high viscosity to resist the slumping. To resist what? The slumping. The flow of the ceramic slumping. To resist the slumping, to maintain a shape during firing. Okay? Okay, ceramic should resist the devitrification. The devitrification means the alignment. The devitrification means means the alignment of the crystals in a manner, in a crystalline manner. So changing lattice structure from a vitreous to a crystalline form. If you don't know what is meant by vitreous and non-vitreous, leave for me a comment asking about it, and I will explain it in a different video, inshallah. Yani, okay, from a vitreous to crystalline form, devitrification. Okay, and surface hardness comparable to that of the enamel. It should be the surface hardness should be compatible of that of the normal enamel to resist or to decrease in wear of the normal opposing tooth structure, to preserve the opposing structure tooth. Okay, we have different classifications of old ceramic restorations according to the construction technique and according to the material. And inshallah, in the coming video, in the next videos, I will explain it and I will show you the different types of old ceramic restorations according to these types. Okay, and inshallah, wait for me in next videos. Don't forget to subscribe. Press subscribe. It's just a subscribe. Press just subscribe and leave for me a comment. Leave me a comment and like, share, and subscribe. And bye.